All right, let's look at part B. Okay, so we're given the series n over n plus 1 times 2 to the n plus 1. It looks to be really complicated to handle this series. To start with, I mean, we're supposed to use the limit comparison test, but just to give you some heads up, because there's not just one way to prove a series is convergent or divergent. I can use another test, in fact, to prove the convergence or divergency. You can pause the video at this moment and you can check that direct comparison test is applicable for this series, because you can majorize the series by a known infinite series, okay? So this is get this as a side problem, and maybe you can start thinking about it after you pause the video. But again, this problem is asking us to use the limit comparison test, so we have to think that way. Okay. All right. So I have n over n plus 1. I'm going to separate this bottom here from those terms. So I'm going to write it as like 1 over 2 to the n plus 1. In fact, I'm going to rewrite this as 1 over 2 to the power of n plus 1. Okay? Well, n over n plus 1, think about it in the limiting sense that it converges to 1. So this series to me is behaving like 1/2 to the power of n minus 1. So I'm going to go ahead and, so this is an, right? I'm going to choose bn to be 1 over 2 to the power of n plus 1. This is going to be my bn. Again, why did I do that? Because this term for larger n's behave like 1 in the limiting sense. So to me, this series behaves like 1/2, or this series, the behavior of this series is dominated by this term rather than this term. Okay. All right. So okay. So what do I know about the series Bn? Okay, that's another question, right? Well, again, the good news is that this series Bn is a known series. You can pause the video and think about what that series could be, but I'm sure like you have already a guess for that. It looks like it's a geometric series, right? It's a geometric series with ratio, we called it R in fact, to be exactly equal to 1/2, which is less than 1. That makes this geometric series convergent. Okay, that's good, because in the next step I'm going to look at an over bn. Okay, the limit of an over bn. If that's a finite number, then I'm going to deduce the same type of behavior for this series. I'm going to go ahead and conclude that the series an is convergent. But there's a side step here. Okay, let's look at that side step. So limit as n approaches infinity, an over bn is equal to limit n over n plus 1 2 to the n minus 1. That's your an. And bn is 1 over 2 to the n plus 1. Okay, so you have two quotients divided by, so you are going to flip the bottom over. Okay, so the good news is that 2 to the n minus 1 cancels out. Okay, so this limit boils down to n over n plus 1. If you pass the limit, it's infinity over infinity, but you know the L'Hopital's rule, right? If you apply the L'Hopital's rule, take the derivative of the top with respect to n, that's 1. Take the derivative of the bottom, that's 1. So 1 over 1 is equal to 1. So there's like different ways to handle this limit, but I just used the most common one, using the L'Hopital's rule, to deduce that infinity over infinity type indeterminate form gets you to 1 as the limit value. So this is your L in the description of the limit comparison test, and that is less than infinity. That means that's finite. Okay, I can go back and conclude that since the limit is finite, both series are convergent because I know this is a convergent infinite series because it's a geometric series. Okay. All right, going back to the discussion here, we essentially use a limit comparison test to deduce that the first series is convergent as well as the second series, and then we just proved that those limits would be less than one, was less than one, and therefore the comparison test works, and the series that we compared, A and B, were like all geometric series, and they were both convergent. So I think that's the end of the deal. Okay. So limit comparison test and the direct comparison test are so similar to each other, but in one case you prove an inequality to start with, and you have to come up with the Bn, by the way, for both tests as well. First you come up with Bn. In direct comparison test, you prove an inequality. In the limit comparison test, you prove this limit, or you just work on this limit essentially. Okay, so whichever is easier for you, use that kind of like test, because these two tests are sort of like brothers and sisters. Okay, so very close to each other. Okay, so it's sort of like up to your taste to use one over the other one. Alright, that ends the video. Thanks for watching. I'll see you in another video. Bye.